Welcome to Chapter 3. We're going to be discussing bivariate relationships, which you probably can guess means two variables. And we're going to talk about how to graph them and also how to interpret some of the statistics. And one thing before we get into all of this is we're going to show things correlate, but that doesn't mean that one causes the other. For that, you need an experiment. So for example, on the first slide, we have eruption duration versus waiting time between eruptions for Old Faithful, which is in Yellowstone and erupts at very frequent intervals. And that's a picture I took a couple years ago while I was there. And it does seem the longer the duration, the longer the waiting time between eruptions was. Now it makes sense because there's probably more water pooling, getting ready for eruptions, but we can't prove, say, one is causing the other until we do further experiments and studies of the phenomena. All right, so 3.1, response variables versus explanatory variables. So the explanatory variable is like your independent variable. It's the one that you are trying to show causes a change in the response variable or the dependent variable. And one is going to be our x, one's going to be our y. So the explanatory is the x, response is the y. And just so you know, calling one explanatory and one response doesn't mean that one causes the other, but we think that one is involved in the change of the other, or that they're both changing at the same rate. Generally, it's obvious which one to make the explanatory and which to make the response. Now, just like in Chapter 1, when you first get data, you want to graph it. Same thing when you get bivariate data, you want to graph it, and we graph it using a scatter plot. And again, your explanatory is going to be on your x, and your response is going to be on your y. So interpreting the scatter plot. Now in Chapter 1, we did SOX, shape, outlier, center, spread. And in this chapter, we're going to do strength, form, and direction. So the strength we're going to get from the R value. So even though we might not know yet if we want to run a linear regression on this, you can run one and see what the R value is, and that'll help you figure out how strong your relationship is. Form, we're either going to say it's linear or nonlinear. And direction is either positive or negative, depending on the slope of what would be considered the line of best fit. So if you have a positive slope, it's a positive direction. If you have a negative slope, it's a negative direction. Finally, we have outliers, and that kind of covers a couple different measurements, the high leverage points and the influential points. And at the end of this slide, we'll talk about those because we don't deal with them as much, but you should recognize what they are. All right, so the first thing here is a rule of thumb, and R it can be positive or negative depending on the slope. So if it's a negative slope, your R is going to be negative. Positive slope, your R is going to be positive. That's why I have here the absolute value of R, because it doesn't matter if it's positive or negative. The absolute value, the magnitude of it, tells you its strength. Now again, these are just rules of thumb. Somebody else might have a little bit different rules of thumb, so you don't have to memorize these exactly, but you should get used to it. Like if I have a 0.7 R, that's a strong R value. If I have a 0, there's no correlation whatsoever. And if I have a 1, there's perfect correlation, and it's probably not real data, it's probably made up. All right, and then correlation, you also want to be careful of doing it with your eyes. That's why we have the R value, because these are two graphs here of the exact same data set. But you can tell this this left one, sorry, is zoomed in, where the right one here is zoomed out, so it looks much tighter. And Therefore, you might say, hey, the right one has a strong correlation, but the left one, this looks a little weaker. However, they're the exact same data, and that's why we have a statistic to help us, because we don't want to have to rely on what our eyes see. All right, so what's this R I've been talking about so much? It's called the coefficient of correlation, and it tells you how strong your correlation is. Here is the formula for it. You're never going to have to do it by hand, but you can see it takes the standardized z value for an x, the standardized z value for the y, and divides it by n minus 1 like standard deviation does. And your calculator, any statistics program will do this. I just wanted you to be able to see it so you kind of can get a grasp for what's going on. So let's do an example in our calculator. It's written out here, so you can pause if you want. I will step you through the different steps to get the R value so you can see what's going on. All right, so we have our calculator here. First thing we want to do is put in some data points. So we go to our stat button and edit. And these are just points I made up. So again, if you want to pause again and type these into your calculator, go ahead. Now, first thing I said to do was plot them. So let's go to second stat plot, and we'll go to plot 1. We are going to do the scatter plot is this first one, so I'm going to enter it. The one that's dark on the very right, that is the normal probability plot from the last chapter. All right, so if you go to the scatter plot, now you have your X list and your Y list, so you put in where your X and Y are. And then you can just hit graph above the arrows. And you go, hey, I have no points. Again, with any statistics thing, a lot of times the graph is not zoomed into the right area. So you can go to zoom and down to number 9 to zoom stat. And now we get our points. And your calculator will always zoom in as far as it can, so this is why you don't want to rely on your eyes. However, the data looks very strong, negative linear relationship. All right, the next step I'm going to show you in order to find R, you only have to do this next step once ever in your calculator's life unless you have to reset it. And that is go to second and 0, which will give you the catalog. And we need to go all the way down to diagnostics on. And that's what tells it to find the R value. And now you haven't done it yet. It's just in the command line, so you have to press enter again, and it should say done. Now we can run a linear regression. So we're going to go to stat, calc, lin reg. Now you'll notice 4 and 8 both say lin reg for linear regression. The only difference is when they find the slope, what variable they assign it to. So it doesn't matter which one you choose as long as you put the number that is supposed to be the slope in front of x. So it doesn't matter. I just do 4 because it's the first one. Then you say the x list is your explanatory, y is the response. We're going to leave frequency list blank. Here you can put in a y in order to save the equation into the y and then graph the line. However, you can just write down the number 2. All right, so here we go. We got our slope is negative 1.19 and our y-intercept is 10.29 and r is negative 0.98, almost 1, which should tell you this is probably made up data, which it very much is. And we'll talk about r squared in another video. But it is just r value and then squared. That's where the number comes from. But the interpretation is more complex. All right, let's go back to these slides. And I just wanted to show you a bunch of different scatter plots. They're all zoomed in the same amount so that you can see the difference between no correlation, negative almost 1 correlation, positive 0.9. So you can kind of see what the difference is. And really, it would be very difficult to get exact 0 correlation. You get some small decimal at least. All right, so I've already talked about this, so I won't belabor the point. Just a couple things to point out. One is that R, because it's using the standardized values, if you change units, it's not going to matter for the R value. So like if you had your measurements for the Old Faithful eruptions, if you had them in seconds and you want to change them to minutes, that's not going to change the R value at all. And you can only get from negative 1 to 1, and those only occur in perfect linear relationships. Normally you'll have a decimal. And lastly, here is the outliers versus high leverage versus influential points. So I will say them verbally, and then I have a picture that, if you're a visual learner, might be more useful. So an outlier is just a data point whose Y value does not follow the general trend of the data. A high leverage point is one that has an extreme X value, so it's either really high or really low. And then an influential point is one that will change the slope of the least squares regression line by a significant amount. And sometimes you can be like high leverage and influential. There are cases where that can happen. So here is a picture. So A is a high leverage point because it's extreme in the X direction, but it's not influential because the slope changes very little with and without that point. And now in B, this triangle is an outlier because based on its X value, it shouldn't be that low on the Y value. However, if you see the red and blue lines, that's the graph with and without that point. So it's not really changing the slope all that much. It's really actually only changing the y-intercept in this, and it's not a huge change. And that's what happens if you have an outlier that's within your data set. It doesn't get that much of a pull because you have all the other data points controlling the line. Then you have, in the last one, C, you have an influential point because it's extreme on both the X and the Y, actually, but it's pulling the line down. So the blue line, the slope is greatly changed from the red line if that point wasn't there. All right, so that's it for 3.1. We will continue this on in the next video.